liquid and solid, okay, it's actually starting from the same origin, right? So partial G, partial P at constant T equals to your volume. Therefore, you know your partial G equals to V partial P. Okay? For the gas, okay, we can always replace the V with P, right? Because for ideal gas, we say the V is equals to RT over P. Okay, so for gas, you can do this. Then you do the integration on both sides. Okay, you get the G equals to G naught plus RT natural log P over P equation, right? But if today you are a solid or liquid, can you do this? If you have a solid or liquid, can you write a V as a function of RT over P? Can you? It's not gas anymore, right? So PV equals RT cannot be used anymore. So can you write this? You cannot, okay? So for the liquid and the gas, you just cannot write this. Okay? So all you can do is actually just do the integration on both sides at this stage. Okay, because you know for liquid and gas, the V is actually not a good function. It's not a function of P anymore. Okay? So all you have is actually your G is equals to V delta P equals to V P final minus P initial. Okay? So delta G you can consider as like G minus G naught, okay? Equals to V P final minus P initial. Therefore you say G equals to G naught plus V P final minus P initial. Okay, so you have similar format, okay? But the second term here is actually not RT natural log P over P naught, but V times P final minus P initial, okay? And for the liquid and the solid, this term, okay, if you look into the values, this term is actually always much less than the G naught. Therefore, you will see in many textbooks, you just say G equals to G naught for the liquid and solid case. Okay? So if today I ask you, you have an ice, okay, at minus 15 degrees C. You have water at minus 15 degrees C, okay? What is the pressure dependence of free energy of the system? Okay? Okay, so the first thing you see is actually H2O and minus 15. You should know this is a solid. Okay. Then, if you want to know the G, all you need to know is actually to check the table to find out what's the G naught of the water. Okay. Then that's the answer to these questions. Okay. If today I say you have H2O and 105 degrees C, what's the G? Okay. In this case, you know it's gas, right? So you should know that G is actually G naught plus RT natural log. If I say this is ideal gas, then you say, okay, I need to know the P, then I can give you the G. Okay? if you say this is actually a non-ideal gas, okay, then I need to calculate what is my F. Once I know my F, I can give you the G. Okay? And how do we determine the F? It's really depending on the equation of states. If the equation of state is this simple, then you know F over P prime follows this relationship. Okay? So to calculate the correct G under different pressure, okay, the first thing you need to know is actually are they gas, liquid or solid? Okay? If it's liquid or solid, then just check out the G naught. Okay? If it is a gas, you need to know it's ideal gas or non-ideal gas. Okay? If it's ideal gas, it's fine. G naught plus RT natural of P over P naught. And done, you get the G. If it's non-ideal gas, it's actually G naught plus RT natural of F of P naught. Then you need to know how the F is related to your P. Okay? So in that case, you're going to need the equation of states to figure out the relationship between F and the P prime. Okay? Alright, so that's pretty much for the pressure dependence of free energy. Okay, so the very last one we want to discuss is actually the temperature dependence of the free energy. Okay, so we want to know partial G, partial T, and constant P. So first thing you want to know, okay, what is this equals to? So what is partial G, partial T, and constant P?
Negative S. Negative S.
Yes, very good. Okay. Where did you get this? Where did you get partial G, partial T, and constant P equal to delta S and minus S? Yeah, so we get that because we know G is a function of pressure and the entropy, right? So ds, dg is equals to negative SdP plus VdP, right? Then you know here this thing is equals to partial G, partial T, and constant P. Okay? So partial G, partial T, and constant P equals to negative S. So that means the temperature dependence of the free energy is actually totally related to your entropy. Okay? Okay. Can you tell me this though? What will it equals to? So we say if you have partial AB, okay, partial however, it's going to, you keep one constant, then you do this. Okay, plus you keep the other constant, and you do this. Okay? So by now you should be very familiar with this concept already, right? It's partial derivative concept. You should know this one very clearly already. Okay? So with this in mind, then you can consider on the top what you have is actually partial G times 1 over t, partial t. Okay? So you are going to keep one constant. Let's say we keep the first term constant g constant. And you need to do partial 1 over t, partial t. Plus, you keep the second term constant times partial g, partial t. Okay, the constant t. Okay, so what's this? This is actually g times this, right? And what's this? So partial g, partial t, and constant p is negative s here. Okay? So negative s, we know g is equal to h minus ts. Okay, so negative s is going to be equal to g minus h over t. Okay, so this I move h to the left and divide by the t. On the right hand side, I'm going to have negative s. Okay, on the other side, g minus h over t. Okay. So if you put negative s into here, okay, you're going to have okay, so this term and this is going to cancel out. Okay, so what you end up with is actually negative h over t squared. Okay, so you can see the temperature dependence of your free energy is related to your entropy. Okay? But if you divide your free energy by the temperature and you find out the temperature dependence of that term, it's related to your enthalpy. Okay? So G is actually correlated to the entropy and enthalpy related to respective to your temperature. Okay, so temperature is going to change both terms. Okay? And sometimes people doesn't like this form, okay? They don't like if you do partial g, partial g over t, partial t, that eventually gives you minus h over t squared. What I like is actually if you do partial g over t, partial 1 over t and constant p. Okay? If you do this derivation yourself, you found actually this term eventually is going to give you just h. So you can know the temperature dependence of your free energy is related to your entropy and enthalpy, right? So if you want to derive the G or express the G as a function of temperature, then you need to know what's the temperature dependence of H and temperature dependence of your S. So you can express the G and find out the temperature dependence of your G. Okay. Okay, so tell me, what's the temperature dependence? What's this? Under constant pressure. This is your CP, right? What's this? What's this? Okay, so how do we get this? So remember previously, if you express the ds as a function of T and T, this is equals to right, this is actually one of the equations to remember, right? We just discussed this. Okay. So partial S, partial T, a constant P that gives you this term. So this is equal to Cp over T. Okay? Therefore, we know if you want to know the temperature dependence of your G, then the better way is actually to express everything using Cp. Okay? So what we are going to do is actually we know dG is going to equals to dH minus TdS. Okay? And dH is basically just Cp dt. Okay? And ds is actually T times summation Cp over T dt. Okay? If you integrate on both sides, you're going to end up with delta G is going to be equals to summation Cp dt minus T summation Cp over T dt. Okay, so it's actually very simple. There's no summation here. Okay, so these tell you the temperature dependence of free energies. Okay, but you can see this free energy is actually all related to your Cp. Once you have the Cp values, okay, at any given temperature, you can just put integration, you can find out what is the delta G at a specific temperature. Okay? So one last very important concept that you need to know is actually the difference between delta G and delta G naught. So you learn these things actually when you do your Gen Chem 2. Okay, so what's the difference between delta G and delta G naught? Okay, so G naught stands for what? The difference in the G on the standard state, right? So when you have a system that reach equilibrium, okay, a system at equilibrium. What's your delta G? What's your delta G?
0.
What's your delta G now? What's your delta G now?
0.
Is this right? Okay. Important thing you need to remember now is actually, so you know when you hit equilibrium, delta G has to equal to 0. This is always true, okay? No matter what you have, once you see the word equilibrium, delta G is equal to 0 for sure. Okay, this is always true, okay? When you see these words, this is what it really means. Okay? Delta G naught. So delta G naught is actually, if you have